You need a microscope to see the laser properly. Here's the output of the microscope on a video screen. The great grey block is the tiny laser. The green underneath is the base it's mounted on, and in the back you can see the wire that powers it. The area that actually lasers is only a tiny part. This semiconductor laser is unusual in that its light is visible. Communications lasers are all in the infrared range, the wavelengths at which fibre is most transparent. You could see the structure of a semiconductor laser more clearly if it was the size of a department store. The laser is made up of layers of various materials, similar to those used in transistors. The thin layer in the middle is the active lasing layer. If you could fly down inside the active layer, it might look a bit like this. Some negative electrons from the electron-rich bottom layer transfer to the top. Their positive opposites, known as holes, move downwards. There they rest until a current is applied which frees large numbers of holes and electrons. The opposites combine and give off photons in the process. Soon there's a build-up of photons, all following exactly the wave patterns started by the first. The ends of the laser reflect the photons back into the active layer. The build-up of photons finally bursts out as a laser beam. Every time the laser flashes its signal, the process is repeated. The photons stimulate more collisions, which produce further photons, all in step, surging through the lasing layer. Add the tiny laser to the fine fibre, and you have the perfect data transmission system. But the early systems weren't exactly perfect. A phone call signal could start from, say, Paddington Station in West London. Travelling with 2,000 other calls simultaneously down the same fibre, the signal would start to deteriorate. It could get no further than Liverpool Street Station, 5 miles away, before it had to be converted back to an electrical signal, cleaned up and retransmitted. The problem lay in the way the light was behaving inside the fibre. Light that takes a zigzag path down a fibre will obviously take longer to arrive than light that goes straight down the middle. Lasers can produce light of both kinds, and the earlier fibres allowed these modes or variations to follow a choice of tracks inside the fibre. Imagine that this block of motorbikes is a pulse of light. The cones mark the edges of the fibre. When the pulse enters the fibre, some of it is bent and bounces off the walls, while some goes straight ahead. Because the core of the fibre has a greater refractive index than the air outside, the light can't actually escape. The result is that the pulse gets spread out and stretched. Now watch what happens if you try to send in 2 pulses, one closely behind the other. This overlapping is called smearing, and the further you try to send the message, the worse it gets. This is what smearing would do to a television signal. The original fibre was called multi-mode because it permitted all these different modes or patterns of light. The answer was a new mono-mode fibre, a fibre with an incredibly fine core. Previous pathways or modes are no longer permitted. It's down the middle or nothing. The signal stays clear. Now, in theory, it's possible to send those same 2,000 calls from Paddington Station all the way to Victoria Station. That's Victoria Station in Manchester, 150 miles without a repeater. So today's fibres are amazingly efficient. The problem is to get a laser to match them. The theory of lasers is that they produce light of one wavelength or colour only, but they don't. Put a prism in the beam to separate the colours, and you can see how many wavelengths you can get out of one krypton laser. Of course, this laser was deliberately tuned to extreme, but getting rid of every single unwanted wavelength is remarkably hard. The light from the semiconductor laser has a peak of brightness at 1300 nanometers. But the light spreads to include shorter wavelength light towards the blue end of the spectrum and up through 4 whole nanometers to the longer wavelengths further into the infrared. And this causes a problem which this short tube train will now demonstrate. Imagine it's a multicolored pulse of light about to enter a fiber. The bluish end of the pulse travels faster down the fiber, the red slower. Hence, the pulse stretches, and smearing happens all over again. The different colors reflecting off this diffraction grating show a way to eliminate these unwanted wavelengths. The surface of the grating is covered in finely etched ridges, seen here under an electron microscope. Such a diffraction grating is incorporated into this British Telecom system, which is called an external cavity laser. It's still based on a tiny semiconductor laser, mounted in here. A diffraction grating is set at an angle to the rest of the apparatus. This angle can be adjusted. Light leaves the laser, passing through a fine tuning plate, and onto the grating, which reflects back only the desired wavelength. The light is now purified. Lasing actually takes place in the gap, or cavity, between the semiconductor and the grating, amplifying the pure wavelength. The spectral width of the cavity laser is now 100 million times narrower. No longer is it whole nanometers wide. You can only measure the width at the much tinier scale of 8 decimal places. So smearing is finally banished. First the fibers had to be improved, then the lasers were refined to match them. Now, at last, the enormous capacity of the system can begin to be exploited.
See bright in the afternoon.
So far, all that has been done is to fire single streams of digital pulses along the fiber, but the new equipment permits more extraordinary possibilities. Because light has an enormous advantage over electricity. It doesn't interfere with itself. Beams can cross each other and even travel the same path without getting mixed up. With tunable lasers, you can actually send different wavelengths simultaneously down the same fiber. It's called optical multiplexing. This demonstration, using visible red, green and blue lasers, shows how the 3 beams can be focused into a single fiber. The 3 laser beams are aimed at a diffraction grating beyond the lens. Blue, green and red circles. The light is bent to another smaller grating, which again bends it through the lens and into the single fiber for transmission. And here's the system in action, now with infrared wavelengths.
And the step liners?
The sausage dog is to make a sort of siphon.
In this British Telecom demonstration, one tiny fibre carries 4 different television channels on 4 separate wavelengths at once. Theoretically, it could be 50,000 channels. To untangle the signals, you simply slide a graded diffraction grating across the beam to reflect only the desired wavelength back along a second fibre to the television set. Suppose you could one day go into a shop and buy a radio that could also receive light. Because light is a much higher frequency than radio, there is space on it to carry millions more channels of data than radio can. You'd have to extend the tuning dial to fit it all in. Of course, the light won't be broadcast, but sent down fibres. But all the latest technologies provide massive capacity, not just for music and speech, but computer data, facsimile, television channels, everything. Not so far in the future, we'll never need to step outdoors. The whole world will come to us, courtesy of a beam of light on a fibre of glass. Light may even get inside our computers.